All right, this is it. Lecture the last. We have a little remaining work to do on recovery, and then we're going to have a conversation about distributed databases and stuff like that, NoSQL, and then just a little bit of wrap up, and that's it, and then we'll be done. Yeah. How many of you guys, is this your last week of classes? Wow. Congratulations. That's awesome. I have to say, you will spend the rest of your life thinking back about your great days in college. So enjoy the last week. It's going to be good. It's going to be good for those of you who aren't finishing. Be grateful because you get more of this. All right, let's talk about Aries. I actually have a full slate today. I don't know if we'll get through all the slides. I'd like to. I already tried to trim them down a little bit. So let's remind ourselves what we talked about last time. The recovery story from Aries has got 3 phases. An analysis that goes to that last checkpoint record, or pair of records, begin and end checkpoint, reads from the end checkpoint record all the state that was in memory, that is to say, the transaction table and the dirty page table, reads those back in, and then runs analysis forward to update the transaction table and dirty page table and bring them to a state that is in correspondence with where we were around the time of crash, or at least around the time of the last log record. After doing analysis, we know what the smallest rec LSN is in that dirty page table. And that is the oldest dirty, or potentially dirty, buffer pool page that we need to redo. Right? So that was something that could have been in memory at the time of crash that didn't get flushed to disk. So we go all the way back to the oldest of those, and we redo essentially everything, although along the way you will recall we don't redo things if we can detect that they were actually successfully done. So everything gets done exactly once, and during redo, before we apply the redo, we see if it's already been done. Right? By the time we're done with the redo phase, we have repeated history, not only all the actions, but also all the undo things that had been done before the crash. All those compensation log records we saw were there to help us continue undoing what was being undone at the time of crash. So we've repeated history not only of the actions, but also of the ongoing aborts at the time of crash. And after the redo phase, we then start undo from the end of the log going backwards in history. In batch, we just start undoing transactions, writing compensation log records as we go in the typical fashion. Right? So we go through the standard abort protocol. We just do it for all the transactions at once in the undo phase. So hopefully that reminds you where we were last time. And what we were going to do today was play out these 2 examples we had and maintain the state of the dirty page table, the transaction table, and the flushed LSN as we go through the behavior of this log history. And so to that end, excuse me, I need a volunteer from the audience. This is a very mechanical job, or it's like an automaton type of job. Yes. All right. Red is a good color. Black might be good too. Excuse me. All right, so folks, we're going to need to have on the board, sorry, what's your name? Karina. Okay, so Karina's going to need to put on the board the state of RAM. So it's just going to be like it is on the screen. So we're going to have a transaction table, which is going to have a list of transactions in it. So it's going to have sort of like 3 columns. And yeah, right, nice and big, that's good. So column 1 is the transaction ID. Column 2 is the last LSN for that transaction. Bigger. And column 3 is the status. Status. Okay. We're going to need a dirty page table. Move it off to the side. Yeah. Call it DPT. Dirty page table. It has a page ID, or page number. Or you can just call it page. And then it's got a rec LSN. And then somewhere off on the side, we've got a variable called flush LSN, which we won't deal with because we're not actually going to push things to the log device in this example, so it's fine. And I think for now, that'll do it. All right. So, folks, Karina's going to be our automaton. We're going to tell her what to write in these tables. Okay, so it's not on her, it's on us. The first thing that happens is these two checkpoint records, begin checkpoint and end checkpoint. Do they affect the transaction table? No, because they're not associated with any transaction. Do they affect the dirty page table? No, because they don't actually manipulate any pages. So that's fine. So we get ourselves to LSN number 10, which is an update from transaction 1, writing P5. So somebody shout out what Karina should write in the transaction table for log sequence number 10. What goes in the transaction table? Transaction ID what? 1. Yes. What's the last LSN of transaction 1? 10, as of this time. And what is the status of transaction 1? If you remember from last lecture, there's 3 choices. Running, committing, aborting. Sorry, running, committing, aborting. It's running. Okay, nice. All right, then is there anything to write in the dirty page table? For log record 10. Yes, what's the page ID? 5. And what's the rec LSN for 5? It's the oldest log record that updated this page since it was brought into memory. 10. Great. All right, that was pretty easy, so good. Awesome. All right, let's move on to log sequence number 20. All right, update. T2 writes page 3. What goes in the transaction table? Transaction 2. What's its last LSN? 20. And its status? Running. You can write R, Karina, if you don't want to. You're very neat, which is good. DPT, dirty page table for log sequence number 20. Do we put something in? Page number 3, rec LSN 20. Okay. Oh, right. These log records, don't forget, have prev LSNs, both of which in this case were null, right? Because they were the first log record for each of these transactions. Okay. Log sequence number 30, T1 abort. Do we change anything in the transaction table? What do we change? Status is now, status of 1 is aborting. So you can update the status of 1 to be aborting. Don't append it, modify it. This is an in-memory data structure, so just modify it, yeah. Although I think, yeah, that's aborting. Great. Any other changes? No other changes? Last LSN for 1 changes. That's right. What should it be now? 30. Any changes to the dirty page table? No, right? This didn't affect any pages. Okay. The prev LSN of 30 is 10 because 10 is the previous log sequence number for transaction 1. All right. So we're going to start undoing things. And in order to undo things, we first have to write a compensation log record because it's right ahead logging. Before we undo, we generate a log record for the undo. Okay, so this log record 40, is transaction 1. It's undoing the behavior of the prev LSN, which is 10. So it's undoing a write on P5. It's essentially modifying P5. All right. So any change to the transaction table for log sequence number 40? What do we change in the transaction table? Last LSN changes to 40 for transaction 1. Awesome. What about the DPT? Remember, this is undoing LSN 10, so it's writing to P5. Do we change something in the DPT? No. Good answer, because the rec LSN reflects that first change we made when we brought it off the disk. It doesn't change when we change it again if it stayed in memory. Okay, so no change to the dirty page table. Great. All right, log record 45. We're done undoing transaction 1, so we write an end log record for T1. Right? So do we change something in the transaction table? What do we do? Louder? Remove T1 from the transaction table. All right. We need no record of T1 anymore. Note that the prev LSN of 45 is 30 because that's a bug. That's a bug. The prev LSN of 45 should be 40. And the prev LSN of It's not a bug. 40 has an undo next LSN, which is null, right? Because CLRs have an undo next LSN, but there's nothing left to undo. I don't know if T1's prev LSN, yeah, it should be 30, right? It's the last real log record for 30, I think. It's not a CLR. Okay. Log sequence number 50. T3 comes along and updates P1. Change to the transaction table. What goes in the transaction table? Transaction 3. We can pop into the transaction table. Last LSN of 50, clearly. Status is clearly running. Dirty page table. Page 1, right? Okay, great. Rec LSN for this is 50, because this is the first change to 1 since it came into memory. And now LSN 60, T2 writes P5. What do we change for T2? We change in the transaction table. What do we change? Last LSN becomes 60. Excellent. Status is still running. In the dirty page table, it wrote P5. Do we change the dirty page table? No, right? Because that rec LSN only changes on the first change when it comes into memory. Now, it might have happened, by the way, that somewhere along the line, the buffer pool flushed one of these pages, taking it out of the dirty page table. I didn't put that in the scenario, okay? If that had happened, we would be updating rec LSNs, right? It just didn't happen to happen. We haven't replaced any pages. All right. Unfortunately, the system crashes now, and we lose all that good stuff on the board. All right, but let's not do that. Don't erase it yet. All right, so that was great. Thank you. Awesome.
When we do 40 and we do CLR undo, and then we change the last LSN, what is that? That doesn't actually undo the page, right? Oh, sorry, the update. So what does that do?
All right, so the question is, rolling back in our minds to log sequence number 40. If you remember correctly, we had T1 in the transaction table. We updated its last LSN to 40, right? And then we changed whatever. So this was a 40. We were at state, like this was 1, and this was 40, and this was aborting, right?
Yeah.
All right. At which point, LSN 40, what were we undoing? We were undoing LSN 10. We were undoing a write to P5, right? So what we were doing is we were changing a value on P5.
But I didn't change the dirty page.
But you didn't change the dirty page table because the rec LSN is that first change you make to 5.
So what does it actually change?
It changes the database.
Oh.
It changes the buffer pool image for page 5. We don't have the buffer pool on the board. That would be extra work. So, okay, yeah. So there was a change. It was to the buffer pool page. Great. All right. This is a thinking automaton. That's good. Awesome. Thank you. So we're going to do one more scenario, which, let's see, it has a prefix of what we did before. So we're not going to play through, what do we need to do? Yep. Trying to decide whether it's worth putting this up on the board again, because the 0 through 60 is the same, right? And then we crash. And when we wake up, maybe we should do this. So I'm going to put this up top. I won't erase it. This has been lost. That was memory, and we just lost it. But just for fun, we'll put it up there. It's like a historical state of memory. So we crash after step 60. And now we start Aries, right? And what does Aries do? It's going to begin the analysis phase. Where do we start the analysis phase from in the log? Checkpoint, right? So we're going to start at log sequence number 5. We're going to read the dirty page table off of it. It was empty at that time, right? We're going to read the transaction table off of it. It was also empty at that time. And we're going to start rolling through the log, going through the changes we should make to reflect the state of the transaction table and the dirty page table. And so as we see a log record that's an update, log record 10, we'll go stick it in the transaction table, set it to 10, etc. You're going to end up, because of that what-if question that we just asked, Karina, this is actually not the state at the time of crash. This was the state at the time of crash, right? All right, sorry. As you go through the log, following the rules that we have in the previous slides for updating the dirty page table and the transaction table, you will regenerate exactly this. All right? So as it turns out, when you go through these rules, when you replay the log in analysis, you'll end up with that state of the transaction table and the dirty page table. You will recreate it. And in this particular case, because the buffer pool never flushed anything, you get exactly the same transaction table and dirty page table that the system had. All right. And so that brings us then to the time where we can do redo. And we're going to redo from when? Where do we start redo? You can look at your notes. It's okay. We don't redo from the checkpoint. We do analysis from the checkpoint. Where do we start our redo? It's the things that might not have made it to the disk, right? What's that? Smallest rec LSN in the dirty page table, which is 10. Or we just look it up. We already figured it out during the analysis phase, right? So we can go now to start redo from 10. We'll do all our redos. We'll even redo 40, which is an undo, right? Because we're repeating history. So we'll redo what's at 40, which is the CLR. And we'll write the end at 45. We'll do our updates 50, 60. That's fine. So 70 is going to pick up with 2 undo. Oh, that's the one thing we need to do while we're doing analysis is we need to compute the 2 undo set. So if you remember correctly, things go into 2 undo. It's the highest LSN of transactions that were not committed at the time of crash, right? So 2 undo is what? What are the LSNs in 2 undo? The highest LSNs of transactions that weren't committed? 50, 60. Yes. Now we can start undo using those last LSNs that are in the transaction table, right? So the first thing we have to do is undo is 60, right? You can remember my interpretive dance from last time. The largest log record we'll look at first is 60. It happens to belong to transaction 2. Okay, so we write a CLR for that undo, which relates to page 5. So now page 5 is already in the buffer pool, so actually we don't change the, this is really now, sorry. After analysis, this is indeed the state of the transaction table and the dirty page table. So when we get to log record 70, we will update this, right? Transaction 2 is now aborting, as is transaction 3, because they're in a 2 undo set. Agreed? So I will be the automaton here. And when we do log sequence number 70, we will update T2, right? Its last LSN is now 70. Okay. And it's updating page 5, right? Because it's undoing 60. Yes? Agreed? And we're going to write an undo next LSN on the CLR. What is the undo next LSN? Well, it's on the slide. It's 20. Why is it 20? Why is 20 the undo next LSN of 70? Yeah?
Because
it's the next thing in the log for T2 that needs to get undone. And we found it because it's the preval SN of 60. If you looked at log record 60, which is the thing we were just undoing, it had a preval SN in it, which I left off the slide. And the preval SN for 60 was 20. So the undo next LSN of 70 is 20. That's the thing to undo next, right? All right. 80, so that removes, by the way, the undo next LSN now goes into 2 undo. So we dealt with 60. We've got to throw 20 in here now, because it's the last LSN of a current transaction. I'm sorry, it's not. It's the next thing to undo in that current transaction. All right, sorry. And then we move on. What's the largest value in 2 undo? It's 50. So we're going to do a CLR. We're going to undo the thing at 50, which belonged to transaction 3. Right? It was on page 1. So transaction 3 gets an update on its last LSN to 80. Yes? And we modify T3, which doesn't mean changing the rec LSN, because that only changes on the first change. Okay? And we go ahead and we do that. What's the undo next LSN for 80, for log record 80? It should be the prevel LSN of 50. What's the prevel LSN of 50? It's transaction 3's previous log record, of which there is none, right? So it's null. So we're done with transaction 3, which is good news. 20 or 50 goes out of to undo. And once you get to a undo next LSN of null, you can write an end log record, which is 85, which I kind of tacked on at the end of this line. So T3 gets an end log record because we have nothing left to undo for it. And we can delete it from the transaction table when we write that end log record. Good? Everybody with me? Oh, man, we crashed again. Man, I hate when that happens. All right. Unfortunately, we also didn't flush anything from the buffer pool, so the database is still empty. So we have to start this whole business over again, okay? You go to the checkpoint at 0. You do redo from where? Where do you start redo? Oldest rec LSN. Well, we're going to do analysis first, all the way through 85, right? But analysis is going to give us that the oldest rec LSN is 10 again. So we're going to redo from 10, and we're going to keep redoing all the way through 85, including the undos. And we're going to pick up right where we left off. And we're going to then undo the remaining things. And the only remaining thing is going to be 20, because that is going to be the... did I erase the wrong thing? I erased the wrong thing. No, I didn't. Sorry. Last LSN here was 70, but 70 was a CLR with an undo next LSN of 20, right? So 20 is going to be the thing that we're going to undo next. Make sense? And so we're going to start undo from 20, and there's going to be one more thing to undo, and then we're going to be done. Okay? And we'll write an end log record for T2 at 95, let's say, and we're finished. All right, so you can see how repeating history works, even if you crash during recovery, right? And you can see how undo writes CLRs, so that repeating history means you only undo things exactly once. Okay? And you can change this example when you study for the final by introducing buffer pool flushes. So if things get pushed down to disk, which I recommend that you do this while you're your study partner, if something gets flushed out of main memory, out of the buffer pool, onto the disk, it will be removed from the dirty page table, right? And it will have the page LSN in it that is the change that last affected it, right? That page you write down to the disk will have a page LSN corresponding to one of these log records. When you bring it back in to the dirty page table, it will have a different rec LSN, right? Because the first change since it got read in is going to be something later. Okay? And you'll have to be careful during redo not to redo the thing that got flushed when you did your buffer pool flush. All right, so I encourage you to go through that scenario with your study partners when you're studying this at the homework. You can take the same log record, but just throw in some buffer pool flushes into this history and see what happens. Okay? That would be one of the main changes I'd recommend when you study. You can take a different scenario as well, but one thing that's not exercised here is that conditional logic around redo that results from flushing during recovery, or even flushing before recovery. The other thing that's not interesting in this example is the begin checkpoint, end checkpoint are obviously empty in this case. We started from the beginning of time. You could try to work through a scenario where they're not empty, but it's a little hard to do. You sort of have to generate a lot of state. All right, questions on this? All right, remember I said that with Aries we were going to walk a very narrow path, which is I will teach you a protocol that works. Don't step to the left or right. Hopefully this was something where you can mechanically reproduce this correct protocol. If you want to think hard about how to make it better or how to change it, I encourage you to do that in your spare time. All right, but maybe after you study for the final because it will only confuse you. All right. Okay. So just some questions. What happens if the system crashes during analysis? When it comes back up, what does it do? Just as analysis again, right? Nothing happens. Analysis actually doesn't do anything but modify some in-memory data structures. Dirty page table, transaction table. What happens if the system crashes during redo? When it wakes up, it does analysis, and then it does redo again, right? Does it lose all the benefits of the previous redo? Anybody? If it crashes during redo, the second time round, was all the work of the previous redo wasted? I hear a yes. In our example, that's true. We lost all our benefits of redo. Is it always going to be lost work? Why not? Good. It's possible that during redo, the buffer pool goes ahead and flushes some pages to the disk, to the database disk. That's goodness. All right, those redo changes will be remembered. And when we go through our redo analysis, you'll remember there were conditions where we didn't have to do the redo. We didn't even have to pull the page up from the redo sometimes if there was a checkpoint since redo. So it's possible that we're doing redo, the buffer pool flushes some stuff. Well, anyway, bottom line is we won't have to redo things twice necessarily because the buffer pool will flush some of our redos the first time around. Okay. How can you limit the amount of work in redo? Suppose we said, man, my database system's configured in a way where when it recovers, it seems to redo lots and lots of stuff. How can we make it redo less stuff next time it crashes? Yeah. Yeah, get that buffer pool to flush stuff. And if you think about it, it's not just flush stuff. It's kind of flush everything. Because remember, we redo from the oldest page in memory that hasn't been flushed in a while. So if you have a hot page like the root of B tree that you look at all the time, it's quite possible that that thing with LRU will stay hot forever because every query touches that page. So you actually need to override LRU a little bit. Say, you know what, we're not going to replace this page, but let's flush it. And so periodically, even the hot pages should be flushed to disk because we don't want there to be any page in memory that's not been flushed in a long time. Right? So that's how we limit our redo expenses, is we make sure to flush all the buffer pool pages with some regularity. Right? And then the oldest thing that's been flushed isn't that old. So we're going to flush asynchronously in the background, and this is particularly important for hot pages that would otherwise stay in memory on their own. How do you limit the amount of work in undo? Oh, question first.
So during this whole process, you go set and do transaction stuff, and you say, wait.
During recovery, haha. So now you're starting to ask interesting questions about how can we make Aries more fun. It is possible to start running transactions while recovering, but it requires care. I will leave it at that. Yes. But that was sort of the second paper from IBM on Aries. There's like 5. There's a lot. There's all sorts of fun stuff about recovering B trees, especially, by the way. All right, undo. How do we limit the amount of work at undo time? Man, I hate undoing things. It's so expensive. How can I limit undo time? Well, what's the oldest thing we might undo? The first log record of what? Something that hasn't yet committed or aborted. It's the first log record of the oldest transaction live in your system is the thing you might have to undo, right? So the only way to limit that is to not let people run really long transactions. If something runs for more than, I don't know how many log records, abort it. Bad transaction, right? So you could do that. That'll limit your undo window. Just avoid long running transactions. Good? All right, if you didn't understand these are not just tuning questions. These are actually questions to kind of get at, did you understand why we start redo where we do? Do you understand why we undo until where we undo? Make sure you understand the answers to these questions because that means you understand kind of the protocol. Okay? All right, to summarize, the recovery manager is this software component that implements all this stuff. It guarantees atomicity by ensuring that if a transaction does not commit, all of its effects are undone. It ensures durability by saying that if a transaction said it would commit, all of the updates that transaction made are reflected in the buffer pool and eventually the database, right? So it ensures that things that shouldn't commit don't, and things that should commit are durable. All right? Write-ahead logging allows us to have this aggressive buffer pool policy where we can steal pages from the buffer pool whenever we like and flush them back down to the disk, even though the transaction hasn't committed. And we can respond to commit requests by only doing a little bit of log I/O. We don't have to force buffer pool pages to disk in order to commit. So it's steal, no force, which is the most flexibility we can give to our buffer pool manager. And write-ahead logging allows us to do that without sacrificing correctness. Remember that log sequence numbers are the key to this whole thing. We have, in essence, introduced a clock into our database. There is one true notion of order of updates of time in the database, and it's the log sequence numbers. And everything is sort of keyed on this order of execution in history. All right, so LSNs identify the log records. They're linked into backwards chains per transaction to give us the history of each transaction. That's what the prev LSN is for, and it lets me do my dance during undo. Right? And the page LSN allows me to compare data pages with history, with the log. So I can see what point in time, in log time, a page in the database is at, and whether I need to redo it, undo it, etc. Right? So every page in the database has a page LSN that ties it back into the history of the log. Right? So the log, in some sense, is truth. The database is a cache with pointers into the history of the log, which is kind of a crazy thing. Once you see that, actually, the next question you want to ask is, maybe I can get rid of the database if it's just a cache. I can have a log-only system. People have tried building things like that. Postgres actually originally had a storage manager that essentially was sort of like that. And if you like, multi-version systems are kind of like a log. Right? We learned multi-version concurrency control. You keep all the versions of the objects. The log is all the versions of the objects, right? Just diffed. So it's kind of like the log is a multi-version database, and the database is a current version cache of the log. That's how it works. It's kind of cool. All right? Oh, the other thing that's really nifty that we learned was the checkpointing scheme, which doesn't take a checkpoint at all, right? It just checkpoints main memory, and it's a quick way to limit the amount of log you scan on recovery. Remember that recovery works in 3 phases: analysis, and then repeating history, redo, where we redo even our undos, and then undos, which pick up from where we left off at the end of redo. All right? As we undo, we continue logging. We're writing CLRs. That allows us to repeat history. That's what CLRs are for. They allow us to repeat history. All right? Redo repeats history. And I will tell you that, you can try to read the Aries journal paper, but they'll talk to you about what would happen if we didn't repeat history, if we skipped all the undos. Because why would we undo something twice, kind of la la la? And it gets really confusing. Repeating history keeps things really simple. And by the time we get to the undo phase, we know exactly where we are. We're just doing plain old transaction aborts, the same way we would if we were running a regular system. And so that's all goodness. All right. Any last questions on recovery? Yeah? So the question was, if we flush pages to disk more often, for example, to limit the amount of redo we need to do, right? Isn't that kind of like force? And I would say it's that's the difference between forcing someone to do something and encouraging them to do it, right? So your parents probably didn't force you to go to college, but they probably did encourage you to go to college, right? It's a big difference, actually, right? So and in the case of the log, it's a difference in real wall clock time. So in order to commit, if you have to have a force policy, that means you can't return that commit record to the user until all of those database pages are written to disk, which could be a lot of random IOs. So encouraging the buffer manager to write more often might slow it down a little bit in terms of sheer throughput, all right? But it doesn't have to do it now. It could do it in a little while. All right? So it's kind of the difference between a background task and an interactive task. Other questions? Yeah. So the question was, could I do a big picture review of analysis, redo, and undo? And I think given time, I'll encourage you to do that in review sessions next week. Yeah, I think that's a big bite of pie to try to take and redo. So it's just a lot of work to go through it again. Yeah. I don't think I can do that in 2 minutes. All right. Well, with that, my apologies for dodging that question. We have one more deck full of slides, and this is it. So we'll go through as much of this as we can. The topic is distributed data, which is an increasingly important topic in our ever-shrinking world. Data replication is the piece of distributed data that makes it interesting, really, and NoSQL systems. Okay? But before we do that, important administrivia. Final exam is Monday, a week from Monday, May 11th. 11:30 to 2:30. So eat your lunch in advance. All right, and do all your bio stuff, both input and output, in advance. Okay, so you can come to the exam, with your log flushed. I have never been in the classroom at the RSF, but apparently there is one. Based on my Googling, I saw a lot of things about where the heck is the thing in the RSF with the classroom. So people in the past on the internet have had a hard time finding this room. I've never found this room before. I've never tried. I encourage everyone to go a little early if you don't know how to. I know where the RSF is. I don't know that there's a big classroom in there. So it's just the basketball court, and they just set up tables. Wow, cool. All right, we can play a little pickup game at the end. So I'll see you at the RSF Fieldhouse. It is a cumulative exam. We will stress things more towards the end of the semester, but not a lot. It's going to be we're going to have coverage of a lot of things. And of course, things at the end of the semester are cumulative with the things from the beginning. You can have 3 crib sheets, so you can use the ones from the midterms. That said, I don't encourage you to do that. I encourage you to re-summarize, right? Remember, it's kind of like the difference between scanning and indexing, right? You want to have your brain be an index of the material, but if you just copy all the material and you don't think it through, you're going to have to scan your notes, right? You want to have a mental index of what's in your notes, and you want your notes then hierarchically to be the next level down index on everything else. So your notes are a summary, your brain is your index. Building that summary will build your mental index, okay? There is a famous quote from Einstein, right? Don't remember anything you can look up, I think. It goes something like that. Unfortunately, on this exam, write down the things you would otherwise have to look up and don't remember anything on your crib notes. Well, no. Remember an index to your crib notes. That's a bad quote. You really should have a mental index of things that at least tells you where to go look. And in this case, it will tell you where to go look in your notes. All right. And the reason for that, to address Dr. Einstein a little bit, if I can have a little debate with Dr. Einstein here, is just about speed of making progress in life. He's kind of kidding, right? Clearly. If you have to do everything from first principles, if you have to look everything up from scratch, you move very, very slowly, right? So the reason to make you do some memorization is so that things get ingrained in your brain, and all the first principle stuff is background knowledge, and you can move forward. So part of the exercise of studying for the exam is to get this stuff to actually soak into your memory cells so that in future you don't have to rederive this stuff or read the Ramakrishnan book from the first page onwards. I've now tried to justify why we give tests. I hope that was good. All right. There will be review sessions. They'll be held here at the usual class times. They will be webcasted. So if you're watching this on TV, you can watch those on TV also. I'm holding office hours at my usual time next week, and then the TAs have posted to Piazza both office hours and discussion section time. So there's going to be quite a few opportunities next week to come ask questions and just listen and soak in material. Okay? So the TA's actually been pretty generous with their hours. They're all taking finals next week too, pretty much. So be nice. Cool. All right. So let's talk about distributed databases and NoSQL and stuff. All right, so this is the outline for what I was hoping to cover today. We'll see if we get all through it. Basics of sort of traditional database replication. Talk about what does it mean for replicas to be consistent. Talk about how you do updates in a distributed replicated database. And then we'll kind of move to the present era. We'll talk about what happens at truly massive scale, like at internet services. What are the performance requirements? Where did NoSQL come from in this environment? And what is its notion of consistency, typically? And then I'll talk a little bit about the reality of living with NoSQL. So how do you write programs when your data might be inconsistent? So there's a bunch of different approaches. They have costs. And there's a result that came out of my group called the Calm theorem that helps you reason about how to write applications correctly in the context of inconsistent infrastructure, which, if we have time, I'll explain to you. And then, I have a little snapshot of kind of some of the things going on in NoSQL today. All right, why would you replicate data anyway? So when I first learned about distributed databases or distributed systems in the early 90s, let's say, it seemed pretty exotic to me that there'd be like a computer in San Francisco and a computer in New York and a computer in Tokyo, and somehow we would want to run transactions on them and store stuff. It's like, that's ridiculous. Just put all the computers in New York in the middle and be done with it. What is this distributed database? Well, here's a couple reasons why you might want to distribute your data. One is to survive catastrophic failures, like earthquakes in San Francisco. All right, now you might argue just put all your databases in some place that doesn't have earthquakes, but I don't know, there's alien attacks and All kinds of things could happen. So to survive catastrophic failures, you want to make sure that you put your data in places that don't have correlated failures, right? Geography is a pretty good correlation for failure. Power grids go down, you get geographic correlation. Natural disasters give you geographic correlation. Civil unrest, which just happened this week, right? You don't want your data center in Baltimore this week, right? So you typically want to geo-replicate somehow. So at the small, that means you want a data item to be on different machines in the rack. And in the large, it means also another copy in another data center, right? So typically, that's kind of the replication you want to think about. That's for availability. That's to make sure there's a live copy of this data up at any given time. The other reason to replicate data is to reduce latency so that a request can be routed to a nearby server. This is particularly important in geo-distributed databases. I don't know if any of you have taken vacations in faraway countries with a limited internet access, but you really don't want to be round-tripping from Australia or South Africa, let's say, to the United States. Right, which is why Google has point of presence in all of these continents. So for geo-distributed data, you want to choose a nearby server. Also, you can play games like issue a request to lots of servers, and whoever responds first is the replica you get. So you can deal with variances in performance, latency variances in performance, by just running a bunch of them, running your request to a bunch of places and taking the first one. Another reason for replication is load balancing. The system internally, you can ask it for a piece of data. It can decide which replica to route you to based on load. Okay, so it's got more than one choice now. And it's been shown theoretically as well as empirically that if you give a scheduler the power of more than one choice, it can do much better in aggregate at dealing with load balancing. There are other reasons to replicate data, including a bunch of sort of administrative concerns in running big systems. So you can read about those as well. All right, so there's lots of good reasons to replicate data. And in large-scale systems that we have today on the internet, many of these, I would say all of these are real concerns. All right, one of the things that we really worry about with replicated data is consistency. And we have to be careful, very careful, to define what we mean here, because people are usually quite sloppy and it leads to all kinds of confusion. What we're talking about today, when we talk about consistency, is replica consistency, which is to say, loosely, I want my replicas to be the same. If I'm going to replicate a data item, I don't want to have different versions, or worse yet, completely unrelated versions in different places. All right? I want to have the same version everywhere. So what we'll typically talk about as a formalization of that is what's called linearizable writes. Not to be confused with serializability. There's a later invention called linearizability. You'd wish they'd come up with a term that was less, sounded the same, but is what they call it. But really, the illusion we want to give is that all copies of data item X are updated atomically. If you're going to update a value, update all the copies at once. If we did that, we would understand what an update means, right? So this is sometimes called a single system image. It's as if you only had a single copy. All right, that's the illusion we want to provide. Much like serializability, we don't actually have to do that. We just have to make it look like we did that. So really what we're going to guarantee is that readers see a value of X that they would have seen in a single system image, all right, at some point, in some schedule on a single system image. All right. So that's what we want to achieve, that readers can't tell that they're in a distributed system based on versions of individual items. All right, this consistency, this replica consistency, which you can go back to thinking about as everybody's got the same version for a minute. This is a simple version of this. This is not to be confused with the C in ACID. Remember what the C in ACID was. That was consistency in terms of integrity constraints. The database starts in a consistent state, meaning it observes the integrity constraints. You run a transaction, and you get a database that still observes the integrity constraints. It's nothing to do with replication, right? It has nothing to do with atomicity of writes. It's all about just checking like foreign key values and any other check constraints you have, okay? So the C in ACID has nothing to do with this consistency. And for the rest of today's lecture, I'm talking about this kind of consistency. Most systems people who aren't sort of well-trained database folks like yourselves, when they talk about consistency, this is what they mean. All right, so don't get confused when people talk about consistency. Or, if you're pedantic, you can say, do you mean consistency as in ACID, or do you mean consistency as in distributed systems? So anyway, you should know that now we're going to be talking about replica consistency. Now, linearizability is also not to be confused with serializability. Okay, we know what serializability is. It was about transactions. It was about you have a whole set of actions for a transaction, and it's as if they ran in isolation, right? That's serializability. Linearizability is only about single actions. It's not about transactions. It's a property of a single write. Right? And all it's saying is that that single write to that single object was atomic. It's a much weaker thing in a sense, but it applies on a different dimension. It applies on the dimension of replicas. Serializability said nothing about replicas, right? So these are just different things. You can build serializability using two-phase locking and two-phase commit and stuff on top of a linearizable store, okay? Because they're separate. The linearizable store then just looks like a single-site database, right? Which happens to have many participants, and you go off and do things. All right. They're different concepts. Questions on linearizability or on consistency in this notion of consistency? Yeah? An action in our case is a write. It's the only action we'll concern ourselves with today. And it's the only action most of the literature concerns itself with. And I will bring exceptions to that if we have time towards the end of the lecture.
And what is the smallest unit of that
Haha.
page or an object?
That's a great question. The question was, what is the atomic unit of writing? Is it a page? Is it a tuple? Is it an object? That is left to the system designer, okay? So we can assume for now that it's a tuple, let's say. Or in the case of a NoSQL system, it's a key, which has a value associated with it, a key-value pair, which is a tuple with two columns. All right. Here's how replication can be achieved. All right. There's sort of two typical ways to do it. And we'll just kind of roll ourselves back into time a little bit and think about traditional databases. So imagine you have a small number of big databases, which is kind of actually what you do have in the real world. You have like data centers, like Amazon, right, has like, I don't know how many data centers, but it's in the order of the number of continents. There's a couple in America, there's a few, but it's something like a dozen. So you have a bunch of big databases, but you have a few big databases, all right? And let's say there's one per continent, and they're replicated for failure recovery mostly, okay? So there's two ways to make sure that they stay replicated. That is to say, when I get updates here, how do I make sure they show up there? One way to do it is to make sure that my data gets copied over there. My data pages, my objects get copied over there. That's called data shipping, all right? And it's kind of a drag, because it means every time I get a write here, I have to do something extra. I have to send it over there. And it also means that over there, I'm constantly being bombarded with requests to write to the database. And we know that like interactive writes to the database are random IOs, and we don't love that. Okay, so data shipping is kind of expensive. Here's another thing that's kind of weird. It's actually kind of hard to get transactional guarantees, even if all the transactions are single site. So if I'm running a bunch of transactions in San Francisco, you're running a bunch of transactions in New York. They don't touch each other's data, and we just want to replicate them back and forth. It's actually hard to get that right if we're shipping arbitrary pages back and forth. Right? The only way to do it is two-phase commit. Right? If you want to commit in New York, you have to talk to San Francisco and say, did you get all my updates? And San Francisco has to say yes, and then you can commit. Right? So that's kind of a drag. So it's expensive to do this and have transactions. A good thing about it is that it's pretty interoperable. So I could be running Oracle in San Francisco, and you could be running IBM DB2 in New York, and we're just shipping data values, and so we can describe that at application level. You know, I had a table, it had this row, I updated a cell in this row, please update it on that side. That can all be said with SQL. Right, you can do that all in a high-level language. So that's good. So easy interoperability. The other way to implement this, instead of shipping the data, is just to ship the logs. So San Francisco keeps spooling off its log to New York, and New York keeps spooling off its log to San Francisco. All right? At the source node, you were writing the log anyway. It costs you very little to have that log device send it off on the side. And you can do it in the background. So you don't have to send that log off immediately. You can send it off periodically. Okay? So it's kind of cheap at the source node. You were writing log records anyhow. The bandwidth is more modest. As we know, writes to the log tends to be diffed, and they're compressed in a nice way, so that comes for free. And then this single node transactional replication comes built in. So San Francisco transactions are happening. I'm generating log records. In New York, you're receiving log records. You see all the behavior of my transaction. You see the begin log record, you see all the update log records, you see the commit log record, and you see the end log record. So you know in New York which transactions from San Francisco you've gotten atomically committed and which ones you're still waiting to hear about. Right? So you know in New York at least something from the past about what was transactionally true in San Francisco, and vice versa. Okay, so you get transactional behavior on these single-site transactions as you replicate them. It's out of date, but it is transactional. And if San Francisco crashes, New York has a valid copy of San Francisco as of a point in time, right? Which is nice, really nice, if you care about transactions. Unfortunately, this is really hard to do across systems. If you're running Postgres over there and I'm running MySQL over here, you got to write a Postgres log sniffer that translates to a MySQL action roll forward thing, which you can just imagine those two open source systems don't have very well documented log APIs, right? And actually, there are companies that have done this for like Oracle and SQL Server and stuff. It's really hard. You got to reverse engineer a commercial database's log, figure out what it's doing, and map it to another commercial database's roll forward logs. And they don't even necessarily have the same semantics. So Oracle's doing snapshot isolation, and DB2's doing serializability. It's a mess. So this is really hard to pull off across systems. So log shaping is super fast. It's nice and transactional, but you need to get into the guts of these logs and the semantics of the transactions at the two sides. All right? Okay. This is one of the reasons that global organizations will go with one vendor sometimes for all this is replication works. Log shipping replication works. All right. Here's another dimension you have to decide on when you're designing a replicated database. Single versus multi-master writes. And this is where things start to get squirrely. So let's step a little bit back from transactions and maybe even back from consistency in the replicated sense. All right? So the question here is, for a given object, tuple, let's say, in the single master solution, every data item, every object has an appointed master node. And maybe that master node is assigned through a hash function, or maybe there's exactly one master node for the whole system, or maybe a table has a master node. However you figure it out, every object has one master. Writes are always sent to the master. The master performs the write first, and then asynchronously propagates those writes to the copies. Okay? And it doesn't have to be that there's a master for all things, right? The mastering of different items could be different, but every item has one master. You can use two-phase locking and two-phase commit to layer transactions on top of this, right? In a very natural way, because all the locks can be set at the masters of the data items, right? This is very easy to understand, right? Very clear. All writes are going to go to well-known places. You can set locks in those well-known places. It's easy to understand. But a lot of the benefits of distributed database get lost, particularly for writers. So writers now have to go to that single master, which is kind of like what we had before of going to the single copy. If there was no replication, the writer would have the same performance behavior, right? I need to write this object. It lives over there, so I have to talk to that guy. If that guy's slow, it doesn't matter that it was replicated. We still have to talk to him because it's single master, right? It also defeats load balancing. If there's a really popular set of items and they're all mastered in the same place, then that node will get all the writes first, right? So it defeats some of the benefits of distributed systems, but it is easy to understand. Since it defeats some of the performance benefits, it's tempting to go to a multi-master system where you can write any copy. Right? So in a multi-master system, find anyone with a replica of this data item and update it. You can imagine mayhem. Okay, so I'll give you an example that maybe resonates with your personal life. You have calendars that you share with your partners, right? And they're not hosted at Google. They're on your laptops, okay? And you start making updates to the calendar. They make updates to the calendar. And you think you're like actually getting meetings scheduled. Haha, then you have to sync your calendars and you realize you have problems, right? So writes, multi-master, it's tempting because it's easy. You can do the writes wherever you want. But the truth is that with replication on all these copies, everything goes fast. All the writers enjoy low latency and load balancing, but it's hard to make sense of things. Because you can have the same item updated in two places. Then you have to ask the question, which update wins? The calendar example is a great one. It's kind of like phantoms. Tuesday at 12 o'clock might be empty. There's no data there. But in essence, you would like to lock that time frame to put your data item in. Meanwhile, someone else is putting a data item in that time frame. That time frame wasn't data. It was just a value in the value domain. So you can have conflicts where there are two writers to something that used to have nothing. The thing didn't exist, and somehow there's a conflict. Okay. So the same item or the same semantic object, meaning like a time slot, could be updated in two places, and it's hard to say who wins. So you have to have rules for resolving conflicts, right? And you have to go and figure out how to resolve those conflicts manually or automatically. Now, you can do two-phase locking and two-phase commit, but to do locking, you have to set a lock everywhere so that nobody tries to update that object. Right? And then, the bottom line is you've defeated the purpose of multi-master because you can't do autonomous local writes. You have to set a lock everywhere before you do your autonomous local write. And so really, transactions and multi-master don't even make sense together. So multi-master is an attractive performance opportunity, but you got to give up transactions to make it make sense. Multi-master is the path to loose consistency, right? Which is, for performance reasons, kind of attractive. All right, just be aware, loose consistency. All right, here's a compromise between single master and multi-master, which is called quorums, or if you like, quora. All right, the idea here is suppose you have n nodes replicating each item. We're going to send our writes not to all the nodes, but to any subset of the nodes of size W. So we'll, if you have 5 nodes, maybe we'll send writes to any 3 of them. All right, and we're going to timestamp our writes. And we'll also send reads to some subset of items, R. So we had 5 nodes. Maybe we write to 3 of them, and we read from 3 of them. If R plus W is greater than or equal to n, our read set and our write set are guaranteed to overlap, and readers will see every write at one of the reads, right? If I write to 3 places out of 5, you read from 3 places out of 5, we will overlap on one of those places, and you will see my write. Make sense? So to ensure that readers see the latest data, you just have to ensure that W plus R is greater than or equal to n. That's called a strict quorum. And in a strict quorum system, you get sort of the moral equivalent of single master, because everybody sees the latest writes. Okay? But you get it without having a single master, right? You can write to any subset of size W. So a typical thing is you set writes and reads to a majority, right? Which is what we did 3 out of 5. Right? So that guarantees W plus R equals n. But another option is to write all, read 1. That's a quorum system as well, right? Or read all, write 1. That works too. Right? Okay. So the advantage is you're not at the mercy of a single master that could be slow. It's relatively easy to recover from a failed node because there's lots of copies of every write. It does give you updates. If you want transactions, you still need two-phase commit and two-phase locking and stuff like that. But it's pretty good. Okay? So quorums are kind of a nice way to bridge the gap between single master and multi-master. All right, but suppose we really want transactions. We're going to need at the end of this to ensure that all the nodes have updates that they like and are willing to commit a transaction, and that would require two-phase commit. Is two-phase commit a bad thing? Is it expensive? Maybe it's not that bad. How expensive is it really to hold a unanimous vote? All we're sending is like one little packet to everybody, and then everybody sends one little packet back, more or less. Well, the latencies of sending that packet depend on your network, right? So if you're in a data center, the switches at the top of your racks in your data center these days are super duper fast and reliable. That stuff's been optimized like crazy. You do not have a bottleneck at the top of the rack in that network that connects all 40-odd machines in the rack. That thing can have as much bandwidth and as little latency as you sort of need. So you can ignore, in a local setting, on a rack, two-phase commit is like no problem at all. All right, let's go to the other extreme, geo-replication. All right, now you're sending something halfway around the world, you start to run into the speed of light and such like constraints. So talk about that on the next slide. All right, so I'll give you some concretes on the speed of light in a minute. But the speed of light is not that fast, unfortunately, when you start looking at long distances. All right, so that's the raw latency. That's how fast it could go to do two-phase commits. The thing is, best case performance is actually not what you see in the real world very often. All right, so when you buy a disk or you buy a network switch and it says here's the latency, here's the throughput, that's always best case. You don't see best case in the real world very much, often because of software, but sometimes because of hardware. So coming to the second half of this slide, much depends on the sort of delay distribution that you see in real life. How often do you see minimum delays versus other lengths of delays? So in hardware, network switches sometimes do funny things. You know very well that magnetic disks, the worst delay, right, is for a big seek. And the best delay is, like sequential scan, is much, much, much faster. So the delay distribution on a magnetic disk is very wide. It's got a high variance. The delay distribution on a flash disk has a much smaller variance. And so you might want to reason about that when you think about how long will it take for something to respond to one of these requests. Is there a disk drive involved? What kind of disk drive? And then software, funny enough, when we did a study of this stuff, and I'll allude to it in this next slide, my students studied a bunch of these systems. One of the causes of failure in a lot of these systems wasn't failure at all. It was machines that had the JVM running that were running the garbage collector. And they were so slow in responding to messages that the software treated them as being down. All right? When you're running a high-throughput, high-performance environment, something like the JVM doing garbage collection looks like failure. That's how slow it is. So the delay distribution of a system built in Java has very high variance because of the garbage collector. If you build it really tight in C or Go or some other language that's not necessarily arbitrarily garbage collected, you can get it to be much smaller variance. Right? However, that depends on your software being really good. In particular, it depends on when you get an event off the network, like a request for a commit, that the handler for that event doesn't do very much computation and doesn't get in the way of other things, doesn't hold locks and so on, right? So you got to write your event handlers to be very small, very tight, just do the minimal amount of work. And that's hard code to write and get correct. Okay, so delay distribution depends a lot on the software you write. All right. So your mileage may vary. But two-phase commit can be expensive or unpredictable if you have high variance performance on this stuff. Now, famously, the internet stopped doing transactions, right? And instead does things like NoSQL. And so for a long time in this class, I'd say, well, look, transactions are great even though Google doesn't do them. So, if you think Google's cool, I'm sorry, like whatever. But not long ago, Google said, we just implemented this geo-replicated transactional database called Spanner. It's awesome. It's like the world's best transactional database. And then everybody's like, well, Google's doing transactions, so now they must be free. Right? Sort of on the theory that anything Google does is good, right? So the funny thing is you got to stare at this paper they wrote for a little bit because it uses two-phase commit and a bunch of other stuff, including synchronized clocks, all kinds of things. But in the end, if you want transactions from it, it's using two-phase commit, okay? And then you stare at this thing, and it really is still, Google lives on the same planet as we do with the same physical constraints, despite having pretty good code. You can only go, the speed of light only lets you go around the world 7 times per second. Right? And when you look at the performance numbers of Spanner for its multi-site commit protocol, which is essentially two-phase commit, it does a mean latency of 103 milliseconds, which means, if you flip that 1 over that, that's 10 transactions per second. Right? That's outrageously slow. This thing can commit 10 transactions per second. I assure you, Google has more than 10 things to do every second. Right? So what we're saying here is that if you really need to do distributed two-phase commit, even with a very mature implementation, okay, assuming Google's mature, and after all, 7 times around the world per second you're not going to do much better than this. You can't do it very often. You got to really keep your transactions to a minimum in a geo-replicated setting. You want to make sure your transactions are local or live with data that is inconsistent. Okay? And so with that, this dude, James Hamilton, who's awesome and kind of looks like a rock star, so he worked on IBM DB2, then he left IBM, went to Microsoft. Originally he was an auto mechanic working on race cars. Then he went to IBM and worked on DB2. And then he went to Microsoft, but he was contractually not allowed to work on databases, so he was part of the NTFS team. He built the file system. And then he ended up working on cloud stuff. And then he went to Amazon where he designed data centers and cooling and power and all that stuff. So he's just seen systems of all scales and sizes over the course of 30 years. So here's this great quote. The first principle of successful scalability is to batter the consistency mechanisms, like two-phase commit, down to a minimum, move them off the critical path. This is my favorite part of the quote. Hide them in a rarely visited corner of the system and make it as hard as possible for application developers to get permission to use them. All right? So, not only is this stuff expensive, but, don't let software engineers use this stuff, for God's sake, right? Especially app developers. This is pretty sobering when you think about it, because I spent this whole semester telling you guys that transactions make life easy for application developers. And what he's saying is, no transactions for application developers. They don't understand the cost. And some of the reason for this is not just that it's slow, but if one thing gets slow, queues start to back up, and other things get slow, and suddenly you have systems that are oscillating wildly in terms of their performance. Right? And so in the same sort of report that this came in, another guy from eBay, Randy Shoup, talked about how they have the same lesson at eBay from the late 2000s, and it's so much worse because of this queues that build up in the data centers of requests. This quote is only relevant if you're a geo-replicated distributed system, right? Which, unless you're one of about 6 companies in the world, you're not. So anything you learn from Google, and I've said this before in this semester, should be taken with a gigantic grain of salt unless you work at like Google or Amazon or Facebook or like 4 other companies. Right? But if you work at, I don't know, even like the NSA, this might not matter. If you work at NASA, this probably doesn't matter. If you work at Bank of America, this probably doesn't matter. Right? There's a lot of places that do a lot of compute where this is not the right thinking. Okay, but there are interesting places where it is the right thinking, and then what? Then what do you do? So that's a pretty interesting question. All right, we got about 15 minutes left this semester. And I got like half a lecture and some wind-up slides. So let's see. I was having so much fun making these slides. What happens next? I'm going to have to prune, obviously, on the fly. Let's do this. Let's talk about NoSQL and eventual consistency and maybe call it a day. So NoSQL, what is it? Well, it was something that kind of people attribute to Amazon as having invented in a system called Dynamo. So the typical NoSQL approach is that you have a very simple data model of keys and values. Think like a hash table or a map in Ruby or a dict in Python or an object in JSON. Okay? So it has a key and it has a value. And you can put and you can get, and that's it. So it's like a database with 2 columns, key and value. Primary key is on key. That's it. Okay? And all you can do is insert and look up single keys. It's a very simple data model. It's more like a memory cell than it is like a database, really, when you think about it. It's like persistent memory cells, right, which have addresses, which are keys. They're usually replicated. Think like 3 replicas per item or maybe a few more. 3 is a typical number. It's usually multi-master, so you can write anywhere. You put your timestamp when you write. Update is acted by the node you write to. So you write to a node, it says, got it, and you're done. There's no 2-phase commit with the other nodes that it's going to replicate to. It replicates in the background, okay? So you don't really know if it's been replicated successfully or not when you trust that node that says, I got it. That update then in the background is gossiped sort of lazily amongst the other replicas. And there's fancy names for this gossiping protocols. There's anti-entropy, which is just silly. I don't know why they call it that. The Amazon paper has this thing called hinted handoff where they try to make the gossip a little more efficient. This is like in the details. Basically, eventually the copies talk to each other. Reads can consult 1 or more replicas. So you can go to 1 or you can go to multiple replicas and just take the first one you get or the best one you get if you care to look at multiple versions. All right? And in some of these systems, you can set up quorums to get linearizability. Right? So you can do a strict quorum and get linearizability in some of the NoSQL systems. Mostly people don't bother with linearizability, though, in these things. They want them to go fast. And so you get weird stuff when you read things. You may not read the latest version. And also, writers can conflict. So they write the same key in 2 different places, different values for the same key. And then they have these weird conflict resolution or merge rules, popular ones being things like last writer wins. Or maybe first writer wins because it was immutable. All right? But then there's a question like, well, who's setting these timestamps? What clock are we using? Do we really trust their clock? Clocks get out of sync. There's no such thing as a global clock in distributed systems. So that's complicated. Sometimes in some of these systems, you can make up your own merge rules, and they might be semantic rules. Like, all of our writes are increments, which means that the merge should just take the max of all the values we've seen, which isn't exactly the same as incrementing, but it's maybe a good thing. So merge maybe is largest. That would be one merge rule. So there's lots of different things you can do for these merge rules. There's no guarantees across objects whatsoever, so forget about transactions. These are just single actions, and even those aren't linearizable. Right? But they do give you something comfortingly called eventual consistency. They all will promise you, it's okay, it's eventually consistent. So what does that mean? Well, Werner Vogels, who heads up the AWS stuff, wrote a paper about this. He's a former professor at Cornell. And his description of eventual consistency is this. If no new updates are made to the object, eventually all accesses will return the latest updated value. Through that gossiping protocol, right? Eventually, every write is going to get gossiped, and the last writer will eventually persist if no one ever writes again. Which in practice means, I don't know what it means, right? Nothing useful. At any point in time, your system has not stopped writes. Right? This is not how the world works. The world doesn't ever get eventual. Right? And this guarantees you roughly nothing. Okay, sounds nice. So here's the kinds of problems you can have. There's two things that people like in distributed systems. They're called safety and liveness. Safety is the idea that nothing bad ever happens. So could something bad happen in an eventually consistent system? Sure, you bet. At any given point in time, the system is bad. Right? It's got multiple versions. You don't know if you're reading the latest one. The versions may conflict. Right? Things could be bad at any snapshot in time. So it's definitely not a safety property. The other property people like are liveness properties, that a good thing eventually happens. So some would say that eventual consistency is a liveness property. Eventually, the system is consistent. All the replicas are the same. But that eventuality never really shows up. Right? It's only sort of true. This is only true in a quiescent, sort of still eventuality that probably never happens. So eventual consistency is not much of a guarantee, and really no SQL systems, unless you configure them to a higher consistency level than eventual, they're not really promising you much. Which leads to the question of how the hell do you break programs on top of this stuff? James Hamilton says you're forced to use this. You're not allowed to have coordination. And Werner Vogel says you're not getting anything meaningful on your guarantees. So how the hell do you write applications that work? Well, there's three answers. One answer is, who cares? Okay, that's a very common answer. The second answer is, very carefully. That's how you write applications, very, very carefully. So you take into account the fact that, gee, when you put something in the key value store, it might not get it right. And then the third one is you use some new theory from Berkeley called CALM. Okay, we won't have time to go into all of these. And in fact, I think I'm going to, well, I'll do one example, and then we'll go on. So the example is the example from the Amazon Dynamo paper, which is kind of a cool paper. It falls into the category of do it very carefully. Okay? First, we'll look at what happens if you don't care, and then we'll look at what happens if you do it carefully. So actually, we're going to, the first example, let's skip this. This is the very carefully version. Here we go. So here's the eventually consistent shopping cart example in the Dynamo paper. So the idea here is eventual consistency, replicated shopping cart. You're shopping on your website, typical Amazon deal. And, okay, let's go shopping. There's two copies of your cart on two different machines in the Amazon backend. And when you send a request to put something in the cart, it gets sent to both of those in an eventually consistent way. All right? So you want to buy an apple. All right? On one machine, it makes it, and it acts you. And on the other one, it's sort of lost in the Amazon internal network for a while. All right, and then you say, I didn't want to buy that apple after all. All right? And that goes to both machines. And so the first machine's like, oh, really? Okay, 0 apples. And the second machine's like, what? Right? And then you say, I want to buy an orange. It goes to both of them, and cool, they both think you got one orange. And then you say, I want to buy an apple. And they both say, okay, one apple, that's great. And then in the fullness of time, oops, that was supposed to be that was a 1, yeah. This guy's like, oh, apple? Great, now you got 2 apples. All right, so it's just an example of the kind of thing that can go wrong. All right, now we got inconsistent behavior. And typically people are like, oh, well, maybe we'll ship you 2 apples. And so the worst case scenario, you call us up, you're like, hey, what's with the apples? And you're like, oh, okay, send it back. And you just deal with it outside the realm of computing. All right, so that's sometimes called apologies or compensation actions, and they often happen outside of computation, and that's cool because at the end of the day, Amazon is not about computer science, it's about making money and about real-world contracts between real people, sort of real people. Jeff Bezos is a real person, right? So the only question here really is how much money does Amazon lose based on returns due to inconsistency? And the answer is, I don't know, it's not that bad maybe. All right, and so you want to reason about that. So that's a perfectly valid way to build computer systems, is to think literally outside the box on the computing, right? What would happen in the real world if your program was broken? Maybe it's okay the way it breaks, but you do have to think about that. Well, here's what the Amazon guys did, though. They did something a little better, and the idea was that they're not going to update values in a key value store at all. So what we saw was updating values in a key value store. Instead, they're going to accumulate logs in the key value store. And what they're going to do is union them up over time. So here's the idea. This clock is rounds of two-phase commit. All right? So you might think that for every item that you click on to buy, we'd do a round of two-phase commit. But they don't do that. You say, Apple, please, and they say, okay. But they don't tick the clock. No two-phase commit. And then you say, orange, please, and they say, okay. And then you say, Apple, please, they say, okay. You say, oh, look, that apple got delivered. Everybody's got the same thing now. Or we didn't delete any apples, but if we had, that would have been okay too, because we would have sent like a not apple, and we would have accumulated that too. And then at the end, you tally how many apples there are, how many not apples there are, right? So you have a -1 apple, you have a +1 apple. You know how to add those up. That's a 0 apple, okay? And if everybody gets the same set of messages to this log in the fullness of time, including proceed to checkout, and everybody knows they've got all the messages, then they can do a two-phase commit. Everybody got all the messages? You bet. Tick that global clock. Pay that two-phase commit. You only did one round of coordination. So you didn't coordinate it on every click on the website. You only coordinated on checkout. And oh, by the way, you probably had to coordinate with the credit card vendor then anyhow. Okay, so that's actually how they did it, which is quite clever. And I'm going to leave you with that. That's an example of application-level reasoning. And notice that it was kind of log-oriented. It was accumulate-only reasoning, which is important. They didn't mutate state. All right, I'm going to leave it at that for distributed systems and NoSQL, and just give you a couple of notes for the end of the semester. Okay? And we'll wrap up. On the final, here's the topics that you don't need to know about that we covered in lecture. This is pretty important. For functional dependencies, you don't need to know what 3NF is trying to achieve, because I was incapable of expressing it to you in any meaningful way. All right, because I don't think there is any way to describe it. You don't need to know about how to do third normal form decomposition, which means you don't need to know about minimal covers. We didn't cover that. You are responsible for what is third normal form. It's a relaxation of BCNF in a particular way. Go look it up. All right, for text search, we didn't talk about crawlers in lecture. We're skipping that. Okay. For data viz, you're not responsible to understand any of the details of Vega whatsoever. For D3, we're not going to ask you to write JavaScript on the final, but you are responsible for the D3 sort of semantic model and how it works, and you should be able to read D3 code, but not Vega. You're not responsible for the 2 guest lectures we had. All right, you're not responsible for today's lecture on data replication and NoSQL. All right, and from the advanced concurrency control lecture, you are not responsible for B-link trees, although I lobbied for it. The TAs overrode me. So I thought it was a cool topic, but they decided that you guys had enough trees going on. So you're not responsible for B-link trees or phantoms. You're not responsible for two-phase commit and distributed concurrency, and you're not responsible for weak isolation. You are responsible for multi-granularity locking, which I teach every year, so it's kind of not an advanced topic anyway. That means intention locks. You are responsible for multi-version concurrency control. Okay? All right. These are some pithy quotes that I will leave you for thinking about how to study. I want to leave you with a couple of sort of trends notes so you can think about as you go out into the field. A lot of you are graduating, taking jobs, kind of things. These data systems are more similar than they are different. People get all hung up about, oh, did you study relational databases? Man, that stuff doesn't matter. NoSQL is changing everything. These things are mostly the same, all right? They have B trees, they have disk layouts, they have oftentimes query languages and optimizers. They're not always that mature, but search engines, file systems, NoSQL, big data, relational, they're all like 75% the same. And what I hope you learned in this class is not a system, but a bunch of principles and tools that you can apply to new things. So you can examine why and how these various systems traded these trade-offs. It's not good, bad. It's decisions people made because of their engineering constraints, right? You can draw connections between ideas that were invented for one system and how they relate to things that were done in the past, and what the things in the past might teach backwards, forwards into the present. And then, having all these toolkits, hopefully you guys are inventing the next class of data systems, and you can mix, match, and innovate in this context. So don't think of these things as siloed, right? You learn concepts, not systems at Berkeley. And I'll tell you that you're living at a very interesting time. Things are really changing, so you'll need to innovate over the course of your career. We're doing things at this cloud scale. We've got multi-core processors. We're dealing with flash memory, which is very different from magnetic disk. A lot of interesting databases fit in RAM, but we still want things like transactional semantics and durability. Okay? So there's an opportunity to revisit and refactor a lot of the stuff you talked about in class. I hope that I trained you guys to roll with the changes and actually drive the changes going forward. So you should be well-grounded but open-minded. Sort of similar note. This is like the moment for data in computer science also, and I think it's not just the moment, it's the transition point. So basically, computer science is becoming a data-driven field. It's much more about the data than the computation. Okay, data is growing exponentially. Don't forget the number of cores is still also growing exponentially, so we're dealing with parallel programming. And parallel programming ends up looking a whole lot like data management. That's why things like MapReduce and Spark are so widely used for distributed programming, because you have to write parallel programs, and you tend to do a better job writing parallel programs thinking data first. So data-centric methods unlock parallelism, the idea of declarative languages, disorderly languages. Obviously, data is really important to pretty much everything these days. We talked about this in the first slide. There's a lot more to data than making money on ads on the web, right? So hopefully you guys will get involved with some of this. Keep in mind, having been Berkeley students and taken this class, you have enormous value in an economic sense. So as of 2011, McKinsey was talking about a shortage coming up of 150-ish thousand employees in data science-related fields. That includes you. So you guys can do whatever you want. That's very unusual, but it presents you with a wide range of options from engineering to lots of other stuff. And I would encourage you to explore other stuff too and work in a whole bunch of contexts, both in terms of what kinds of things you're building and also what kinds of companies you're joining. It's all about data all over the industry. My company's hiring, for example. So give me a call. My only plug all semester. I was pretty good. And then in terms of value, you also have enormous potential. So what do you want to do next? There's lots of things you could do. Grad school, times have never been better. There didn't used to be a lot of data-centric computing in research. Now it's pretty much everywhere. So you didn't used to be able to go to MIT and study database or data-centric stuff. Now you can. And there's exciting crossovers of data stuff to other areas. And then increasingly, there's chances to work for nonprofits and do really interesting things with data, and you guys have the skills to do that. So I'd encourage you to look at organizations like DataKind and Code for America. We did some work in this space that hopefully can be inspirational you can read about. And then, if you want to learn more at Berkeley, for those of you who are sticking around, there are grad classes. I don't know that 262A, which is the 262B. Some of you are in 262A, right? Like in this class. 262A, yes, that's right. That's the systems class. That will be taught in the fall. It's a joint operating systems database graduate course. It's the intro course for most applied PhD students at Berkeley. And if you're interested in graduate school as an undergrad, I encourage you, this would be the course I would most encourage you to take. I'm not teaching it this year, but I often have. It's a great course. And then 286B is the graduate database course. That I taught last fall, and I don't know if it's being offered next year. But in the meantime, there's at least 3 relevant seminars that run every week, graduate seminars. The database seminar, the SysML seminar, which is Systems and Machine Learning, and the AmpLab seminar. You can get on mailing lists for those you can send me an email to ask how to do that, or you can just kind of Google around for it. Usually in the fall, there's a bunch of 194s. Jan Stoika, who is one of the leading people in the Spark group and runs Databricks, Jan is offering a big data 194 in the fall. There's a bunch of MOOCs going up. I had a 194 on programming the cloud we may revisit at some point. So lots of interesting things. And I don't know what else to say. That's kind of it. So thanks, everybody. It's been fun. Have a great summer. Good luck on the final. And for those of you who are leaving, stay in touch.